Welcome back to another explainer. Today, we're diving headfirst into the massive computational engine that's literally powering modern artificial intelligence, and we're going to uncover exactly how engineers are optimizing it. Drawing on the curated focus of Dr. Srikanth Nalenthikal, we'll be exploring the absolutely fascinating world of deep neural network processing and the specialized hardware making it all possible.
We constantly see AI outperforming humans in stuff like autonomous driving, playing insanely complex games, and even medical diagnostics. But here's the catch. There is a colossal hidden energy cost behind these systems. We all love the magic of AI, right? But we rarely stop to think about the massive power bill required to actually run it.
To really wrap our heads around why that power bill is so incredibly high, we've got to look at the sheer volume of data involved. To train these powerful AI representations, we need massive data sets. Just consider this staggering number for a second. 300 hours of video are uploaded to YouTube every single minute. Processing that level of information requires immense computational complexity. All right, let's jump into Section 1, the hidden cost of AI. So, it all essentially comes down to deep neural networks, or DNNs. Unlike older computing methods that relied on handcrafted rules, rules explicitly designed by human experts, DNNs actually learn their representations directly from the raw input space. They use statistical learning over vast amounts of data. This makes them incredibly accurate, but, as you might guess, incredibly heavy on compute. Looking at the structure here, you can see how data passes through multiply dimensional layers. It starts at the input layer, works its way through the hidden layers, and finally reaches the output layer. Making just a single prediction requires millions, sometimes literally billions of multiply and accumulate operations. It's essentially endless rounds of complex addition and multiplication happening all at once. Now, historically, we just relied on general-purpose compute engines to handle all this heavy math. But the waning days of Moore's Law mean we can no longer just sit back and wait for chips to naturally get faster. We are quite literally hitting a physical limit in traditional manufacturing. And what that means is we desperately need specialized hardware to keep up with AI's exponential growth. Which brings us to Section 2, the data movement villain. So what's actually draining all this battery power? Well, here is the crucial bottleneck. Fetching data from off-chip DRAM consumes significantly more energy than the actual mathematical computations. Think about that for a second. Moving the data around, like fetching weights and pixels from main memory, costs way more energy than doing the math itself. The computation is cheap. It's the transportation that absolutely kills your battery. While general-purpose chips like GPUs are great because they offer high parallelism to crunch numbers, they aren't the whole solution here. Specialized hardware, known as application-specific integrated circuits, or ASICs, are custom designed to minimize this really expensive data movement. By keeping data localized, they become the absolute heroes we need for embedded devices, smartphones, and robotics, where battery life is, strictly limited. And that perfectly tees up Section 3, hardware to the rescue. Let's look at a fascinating, real-world solution to this exact data movement problem. It's an accelerator chip called Iris. Now, Iris is brilliant because it doesn't just focus on the math. Instead, it uses a spatial architecture with 168 individual processing elements, physically built to conquer our data movement villain by keeping the data as close to the computation as humanly possible. It actually achieves this through a 4-level memory hierarchy. Think of this kind of like cooking in your kitchen. Instead of walking all the way down the street to the grocery store, which represents the off-chip DRAM, for every single slice of tomato, Iris keeps the ingredients right there on the cutting board in local scratch pads. If an ingredient isn't there, it checks the pantry, which is the global buffer. Basically, it dynamically avoids that super expensive trip to the store. To make this entire setup work seamlessly, Iris uses what's called a row stationary data flow. This is basically the magic choreography that tells all 168 processors exactly how to pass data to one another. It reconfigures the map of the computation to maximally reuse data locally. The result? Incredible throughput without instantly draining the battery. All right, moving on to Section 4, shrinking the AI brain. But, fixing the hardware is really only half the battle here. We also need to make the software itself smarter. It turns out that deep learning models are inherently over-parameterized. Basically, a lot of the connections in a neural network aren't actually doing much heavy lifting. Because of this, we can mathematically prune them. We can just cut out the redundant weights to save massive amounts of processing power, all while perfectly preserving the network's accuracy. There are a couple of main ways to do this pruning. First, there's unstructured pruning, which removes individual weights based on their size. While that sounds great on paper, it leaves chaotic, irregular gaps in the data matrices, making it pretty tough for parallel hardware to process efficiently. Structured pruning, on the other hand, is much smarter. It removes entire contiguous blocks, like whole channels or nodes. This maintains a beautifully dense, neat matrix structure, which allows our hardware to crunch the numbers in a highly organized and efficient way. By organizing those remaining weights into a nice, structured format, the hardware can truly thrive. Chips like Iris use clever techniques like data gating. That means if the chip detects a 0 value, the hardware simply powers down for a cycle. It skips the calculation entirely, drastically boosting energy efficiency. It's a real game changer.
And that leads us to our final section, Section 5, the future of co-design. Here's the big takeaway. True energy efficiency requires joint hardware design and deep neural network algorithm changes working together in perfect harmony. We just can't design software in a vacuum anymore. Today, researchers are building neural networks specifically tailored to the unique memory hierarchies and data flows of the physical chips they're ultimately going to run on. When we look at the real-world trade-offs mapped out here, it's pretty striking. Applying energy-aware pruning to models like AlexNet, which are those red squares you're seeing, dramatically shifts them to the left of the chart. In that leftward shift, that represents massive power savings and normalized energy consumption, all while entirely preserving their top-tier accuracy. Which brings us to a final, pretty big question to wrap up this explainer. As algorithms grow exponentially larger, will our hardware actually be able to keep up? The quest for efficiency is a constant game of leapfrog, but understanding these hardware-software bottlenecks, optimizing data movement, and pruning the models, that is exactly how we'll push AI out of those massive cloud server farms and into every single device in our world. Thanks so much for joining me on this deep dive.